knowledge of where the electrons are isn't the only thing that we're worried about. It's really not too much of what we're worried about. We're interested in what happens when we put these atoms that maybe have different numbers of protons, neutrons, and electrons in close proximity to each other. How do these things interact? That allows us to get to the chemical properties. To understand chemical properties, the first and really one of the more important things we need to know is something called valence electrons. And that's going to be the topic of today's lecture. Sorry. We'll slow off the draw there. Okay, so here we are. We have our notes in front of us. We also have in front of us a periodic table. I'm going to be referring to this throughout the lecture. This periodic table should be in various places on the drive. This is the periodic table that I would typically recommend students use when they take in-class exams and that sort of thing. We're going to be doing some drawing on this periodic table, and so if you have access to one that you can make notes on, that would be, I think, helpful, especially for taking exams and solving problems and that sort of things. Before we do that, though, let's start to define some of these important terms. So I mentioned this is one of the more important terms to understand if we're going to understand chemical properties, and that's true. Valence electrons. These are the electrons in the outermost shell of an atom. Okay, so kind of an interesting definition. What is the outermost shell of an atom? I mean, can't all atoms have at least 4 shells? That's what we've talked about, maybe more shells, depending on the number of electrons. I mean, we could exceed 32 plus 18 plus 8 plus 2, right? So can't we get into a 5th, 6th, maybe even a 7th shell? Sure, in theory or virtually. But what we're looking at is we want to think about the electrons that are actually there, and the ones that are the most reactive or most likely to engage in a reaction will be in the outermost shell that has electrons. So sometimes the outermost shell is going to be the first shell, as in the case with hydrogen and helium. Sometimes it's going to be, and many times what we're going to look at in this class, it's going to be the second shell, sometimes the third shell, but for the most part, that second shell. So valence electrons are the electrons that would be, in many cases, that second shell. Okay, so the reason why we want to do this again is these electrons are most likely to react. And if they're most likely to react, that is to engage in a chemical reaction, they, for the most part, control the chemical properties of an atom. Okay, so let's start to identify these things. If we had our go to C12, carbon 12 with a neutral charge, 0 charge, we have said before that the electron configuration is 1s2, 2s2, 2px, 2py, 2pz. I'm going to put 1 in the px and 1 in the py. You can flip those around if you need to. But I want to ask the question, how many, changing the term up here, not total electrons, but valence electrons, does C12, oh boy, C12O have? And the answer is, if we look at valence electrons, that's going to be the electrons that are in the outermost shell. And the outermost shell is the shell furthest from the nucleus, the highest numbered shell that actually has electrons. Okay, there are no electrons in the 3rd and 4th shell and beyond for this particular atom, so we're sticking with just the second shell. We have 2 in the 2s, 1 in the 2px, 1 in the 2py, for a grand total of 4 valence electrons. 4 valence electrons, okay? That gets highlighted. That is something that we need to be able to do, to go from an electron configuration to determining the number of valence electrons. And really, honestly, for a lot of the atoms that we're going to work with, carbon being the most important, hydrogen being the second most important, you're going to have to just sort of memorize. And you will just through practice, but you'll need to know the true number of valence electrons around these atoms. So it's 4 for carbon, okay? I know it has 6 total. Those 2 that are closer to the nucleus in that first shell aren't that reactive and aren't that useful. So let's look at sodium, 0, and we'll pick on 23, sure. Okay, we did this one last time too. 1s2, 2s2, 2px, 2py, 2pz, 3s1. Now, our valence shell is the third shell. The third shell is now the valence shell because it has 1 electron in it, and it's the shell that's furthest away from the nucleus or has the highest numbered shell. And if that is our valence shell, then we have 1 valence electron. 1 valence electron in the outermost shell. Now it turns out that a little pattern emerges, a pattern that we haven't really seen yet, and that is that neutral elements will have a number of valence electrons that matches their periodic table group number. Matches their periodic table group number. And the periodic table group number, that is the column number. Okay, the column number. Okay, so let's go ahead and sort of sketch a periodic table. Now this is a really important concept, that the periodic table column or group number matches the number of valence electrons in an atom. But let's be careful and understand that this works for only so many elements. It works for several important elements, but not necessarily every single element. So what I'm doing now, and hopefully you're sort of keeping up with me, is what you're doing now is that we are sketching a periodic table. So 3, there we go. So we have a periodic table here with a bunch of blocks, and how this works is we're going to go have helium, neon. Feel free to refer back to the periodic table if you don't want to sketch this again. Cl, O, S, N, P, C, S, I, A, L, B, beryllium, magnesium, Na, Li, and H. Okay. So these are the elements of the periodic table that I really want to worry about. And what I'm going to do is I'm going to write a number, an important number, below each of these. If you look, I'm just counting up from 1 to 8. And this number is the group. I really like the word group. I would really like it if you knew the word group. If you took a traditional freshman chemistry course, we would talk about group in periodic trends in detail. We don't have that kind of time, but we're going to know the term group is synonymous with column. It's equal to column. The number is the group number, but this is also the number of electrons for a neutral element. Okay, so what I would say is that if we look at this, Na is in group, see if you can find it. I'm going to sketch it once and then erase it. You look at that, it's in group 1, right? There's sodium. it's in group 1, and as a result, it has 1 valence electron. All we had to do was use our periodic table, and that allowed us to avoid having to determine the electron configuration and then look at that outermost shell. Think about the amount of work that saves for us if we just have this pattern down, okay? Instead of having to first figure out how many electrons we have total, okay? If we recognize that it's neutral, we can use this trick right away. But figuring out the number of electrons that we had total, which I think we said was 11, okay? And then we do the electron configuration, 1s2, 2s2, will of V's a jerk, so 2px2, 2py2, 2pz2, 3s1, okay? All to just figure out that the number 1 is the number of valence electrons we have. That is just shown already in the periodic table. Similarly for carbon, carbon is in group 4. So it has 4 valence electrons. And in case you don't see that, let me like do a lasso or something here. So we have, that's the sort of connection I would want you to see. Now, there are some things that we will, that we should discuss, some periodic trends that we should make note of. This will help us get a sense for how chemical properties start to emerge from the number of valence electrons. So looking at some common groups, what I want us to recognize is that groups 1 and 2 are mostly, and really by mostly, I'm just saying not H, metals. Okay, these things are metals. Groups, I'm going to also put 1 and 2 and 3 here. Okay, groups, let's just stick with one at a time. Group 7 is the halogens. This is going to be fluorine, chlorine, bromine, and iodine. We're going to do a lot with those in this course. And group 8 is I don't like that, is the, has the noble elements. I had to be careful in my spelling there. This is noble as though they are of nobility, or they are noble in character, not Nobel as in the Nobel Prize. So these are our noble elements, and this is going to be helium, neon, argon, and then they get less noble as we go down the periodic table, but still important to mention. Okay. So group 8, these are some groups that I want us to be aware of. Okay, 1, 2, 3, these are mostly metallic. We're not going to touch these too much except when we just need a metal around to often counter a negative charge, as it turns out. Group 7 we're going to encounter quite a bit of. These are the halogens. Certainly 4, 5, and 6 are important groups, but we don't need to mention their names too much right now. Group 8, these are the noble elements, and these are some important elements, okay? It turns out that group 8 elements are mostly unreactive. Okay, mostly unreactive. Now, the best case example of this is hydrogen versus helium, okay? So hydrogen and helium, these elements as they exist commonly in nature, hydrogen as H2, helium as just helium, okay? They are both gases and they are both less dense than air. And as a result, being less dense than air and being a gas means we could use them to accomplish flotation and sort of pick things up. So for example, we could have helium balloons that just rise up in the air and they're sort of fun. We could also do the exact same thing with hydrogen. It would float just as well. Hydrogen has this other aspect though. It's not as noble as the noble element helium, And as a result, it has some chemical properties, some reactive properties. In particular, the most common one is the combustion reaction. It participates in combustion reactions. Think back, we actually know that. We've balanced those equations. And it can undergo a combustion reaction, which is not a great thing for something that we want just floating in the air. In the Hindenburg, one of these really engineering marvels to put that much hydrogen into a balloon and allow it to pick people up, that was great, except that it crashed and exploded into a ball of fire. Replacing that with helium, we have a noble element, an element that actually maintains its character and is not likely to react. So hydrogen versus helium, we have something that is unreactive, whereas hydrogen is itself highly reactive, whether it's by itself or tied up as H2. Okay, so when I say noble, I mean unreactive. And another word for that is inert. So these noble elements mostly just stay as noble elements. So helium and neon, don't know why I've got helium, neon, and argon in particular are unreactive. We have several instruments upstairs. I guess on this floor where I'm recording, we have several instruments in this building that we use helium as a carrier gas. It allows us to carry reactive molecules through an analysis process, and the helium actually doesn't participate in the analysis. We often take reactions that are sensitive to air and moisture and blanket the headspace above the reaction with argon. Argon, it turns out, is a little bit more dense than air, so we can push all of the reactive oxygen and moisture in the air away and replace it with the more dense gas argon. Okay, so we've got helium, neon, and argon as these unreactive species. Now, the reason why they are unreactive is related to our discussion So why are they unreactive? They have, quote, full valence shells. Full valence shells. Now that's an important term to appreciate. That is to say, if you look at the helium electron configuration, it's 1s2. That first shell for helium is full. Argon, it turns out, has got 3s2. Let's stick with neon. Neon's going to be an easier example. So neon, 2px2, 2py2, 2pz2, it has a full shell of electrons. But what about argon? Well, argon actually is highly reactive and is very noble, but starts to break that. If we look at the valence shell, which is the third shell, it has an identical electron configuration, except it skips one. By going down one row, we increase the orbital shell that we have for valence. Turns out that 3d0, we have 3d0. This is still considered a noble element despite having several empty orbitals within its outer shell. And that's because these are the d orbitals that are a bit higher in energy. They're actually higher in energy than the 4s orbital. As many of you may be aware, we actually will fill the 4s orbital before we jump into the d orbital. But don't worry about the d orbital. Argon is still a noble element. Argon is still a noble element. Okay, so those are our noble elements, but more importantly, that is how we use the periodic table to predict the number of valence electrons. That's a nice skill to have. And so what I would do is take out a periodic table, maybe the one that's appended to the beginning of the notes, And then there's a bunch of stuff written on there. I would cross out a lot of it and just above the columns, above the groups in the periodic table. I would cross out much of it and just write group 1, group 2, skip a big chunk of it, group 3 for aluminum, and then all the way up to 8, just going to the end of the periodic table. This would be really helpful for solving problems because you can just look at the atom, refer to the periodic table, know exactly how many valence electrons that it has.